Let's take a look at this puzzler. This looks like a very simple, straightforward program, but as you will see, the results are kind of unexpected. So we say double A is equal to 1.0, double B is equal to 0.9, double C is equal to A minus B. All we're doing is a simple subtraction, and this should give C is 0.1, you would think. Turns out that's not what happens, so let's try this out. And we want to see why something so simple breaks, quote unquote breaks. That's actually not breaking. This is doing exactly what we're telling it to do, that doesn't match what we think Java should give us. Okay, so let's set this up. So we say double A is equal to 1.0, double B is equal to 0.9, and double C is equal to A minus B. Very simple. Alright, and then we say we won't print out A and B. Well, we can, but let's just print out C. C is C. Alright, save that and let's print it. And lo and behold, we don't get 0.1, we get something close. We get 0.09999999998. A whole bunch of 9s and then an 8. Why can't it just print out a 0.1? It turns out that 0.1 is a number that's kind of hard to represent precisely, given the hardware that we have these days. So we've had this kind of floating point arithmetic for a long time, for many years, and we have not found a fix for something as simple as 1 minus 0.9. It still gives us something that's a little bit off. Now you might say, well, this is fine, I can live with that. The problem comes about if you try to do something like this. If C equals to 0.1, we can print out system.out.println. It works. Else we print out system.out.println does not work. So let's say we set up some code where we need the value of C to be exactly 0.1 for whatever reason. And we think, okay, we're going to subtract 0.9 from 1.0, and yeah, so we should, if we just look at this code, when we don't see, if you don't look at what the value is that's printed by this statement, we might think, okay, at this point C is A minus B, 1 minus 0.9, that's 0.1. Put in an if statement to, let's say, do some processing, and here we just have print lines, and look what happens. It says it does not work. So this is definitely false. C is not 0.1. And if you're not convinced, you can try. There's a bunch of other numbers that this kind of test will fail on. And I say fail, but this is how computers have worked for a long time, and most of the time this is well understood. Most programmers know that there are limitations with floating point numbers. So we'll print out A and B as well, just to make sure that this is not some magic trick, magic Java tricks. A is 1, B is 0.9, C is pretty close to 1 but not exactly equal. So a very important thing to keep in mind. And this is true, there's a lot of numbers like this. So let's try another one, 0.8. Let's see what happens. Not that good either. Okay, oops, this should be checking for 0.2. Let's try that again. Okay, does not work because we're checking for 0.2 when it's actually 0.1999, many 9s. Pretty close, but not exact. Okay, Okay, once again, why is this happening? Why are we not able to do something as simple as the difference of two doubles and get the right value? The reason is there are an infinite number of double precision, infinite number of real numbers, which we cannot represent all of that complexity with the finite precision that we have with Java. Even though this is double precision, this is supposed to be super precise, still not good enough to represent 0.1, amazingly. Okay, another limitation, this time of ints. We get the maximum value that you can hold in an integer, and we print it out, and it's something like 2 billion. Then we add 1 to it, and what do we get? We get something very surprising. If you haven't seen this before, it is pretty surprising. So I'm going to get rid of this and set up an int. Value is integer dot max value, and I'll print it out. Line the max int is plus value. Alright, and then what we'll do is we can use a different variable. Increment is equal to value plus 1, and then we print out this new value. Increment, and we'll say something like adding 1 gives us, oops. Alright, so if you haven't seen this before, it's a little disconcerting actually, but let's see what happens. Save it and run it. Okay, so the max int is something close to 3 billion. So here's 3 digits, another 3, and then followed by another 3. So it's 2.147 billion. Here's what's surprising. You add 1 to this huge number, this number that's bigger than 2 billion, and you get a negative number. And that's pretty close in value to the positive number. And so this is something that's seen anytime you have computer hardware. You will see this kind of a phenomena. You go up to a very large value, you add 1 to it, just a single 1. You would think it should be able to handle it, right? It can handle a number as large as 2,147,480,647. What's adding 1 to it? What harm can that do? What could go wrong? It turns out you add 1 to this large positive number and you get a large negative number, or a very small number, the smallest number that you can represent in an integer. So why does it work like that? The exact reason for this we will come across when we take computer science 355, it's computer organization and assembly language. Then we will see how hardware works and why this is just something that everybody takes for granted. This is what integers represented in hardware will do. This is a hardware limitation of using 4 bytes to represent a single int. If you wanted larger numbers, you can always use long, but eventually you run into the same problem with long numbers. So if you were to say something like this, right? Long, you change the type, you use a different type, and run this, you still get that. All right. We have to make this one long too by using an L. So it's kind of hard to read. It's 1L. What I'm doing there is I'm making this a long number, and when you add 2 things, you can promote one thing to the other. In this case, we can promote this int value to a long, and this whole thing is a long, and then we store this long in this result of this long addition into increment. try this, and now we get what we think should be the right value. So we had to do a bunch of things. Eventually we got what we think should be the right answer of adding a large positive number and a 1. So you might think, okay, that's fixed it. No, not really, because eventually you would run across the same limitation of longs. So let's just take a quick look at that. You can say long dot max value. Okay. Okay, let's try this out. And you can see that the number is bigger. The long dot max value is 9. It's a huge number. And you might think, well, what can go wrong if we add 1 to it? Well, you get a large negative number, or the very smallest number that you can have with a long. So the same limitation occurs with long that we had with int. And you can go the other way. Short. You can get short dot max value, I believe. Yeah, it didn't give us a error message. And here this should be 1, not long. Okay, so now I'm stuck because I'm not sure how to represent a 1 as a short except by casting it. And even that's not working. Well, I'm gonna have to give up. But you can, you should be able to do the same kind of thing. You should be able to say short value is equal to the max value in a short, which is something like 32,767, something like that. And you should be able to add 1 to it, but I am not able to figure out how to do it right now, unfortunately. Let's try plus plus. Okay, that works. But actually, don't do that. Alright, so we can use, you can use pre-increment. Let's see what that gives us. Same kind of thing. The max, oops, in this case it's a short. The max short is 32,767. Adding 1 gives us a negative number that's pretty close in value. And so this is the smallest number or the largest negative number that we can represent using a short. Okay, so take a look at this. Try it out. The same problem occurs with ints, with longs, and with shorts. The limits are different, but it's essentially that's the same problem. It's a hardware limitation. We're using a finite number of bits to represent each one of these things. Okay, so you might say, well, why are we learning about things that don't work? Well, you have to know how to use this properly, or you might run into bugs that you might spend days trying to figure out why you have a large positive value in an I, and you add something as small as 1 and you get a negative value. Why is that? Well, that's the limitations of hardware. And every programmer should be aware of these limitations. Okay, so next up we'll take a look at a more sort of focused look at values and types in Java.